This chapter, set theory, or this subject set theory, is very important, and it is also very fundamental, and that's why it is very important. What is a set? Set is a collection of distinct elements. Okay, so consider anywhere where you have different elements that are distinct. You can think of it, all of those elements, and you can fit it into one place. Okay, then you name it. That is a set. So you are just concerned with the elements. You are just concerned with the distinct elements, and not in the order that you are collecting them. So this is what a set is. A set is a collection of distinct elements. For example, think about university. In the context of university, all students are distinct. Okay, so you can just put all of the students into one entity and call it a set of students. You want to pet a cat, and you go to a shop, and you ask the shopkeeper, what are the different breeds of cats. Now each breed is distinct, and because all of the breeds are distinct, then you put them into one entity called as breeds of cats, and in it each element is nothing but the different breed of cats. And set is very important, because building upon set theory, other concepts are derived. For example, the counting principles. Okay, in combinatorics, we will see that in combinatorics we are looking to find out the ways of doing things, in what ways, in how many ways you can achieve this operation, achieve this task. There also, each way is one distinct element. Each way is one distinct element. Let's say you have to perform two tasks, task 1 and task 2. And if you perform both the tasks, if you perform both the tasks, task 1 and task 2, then your objective is supposed to be fulfilled. Now, there is a set which includes the ways to perform task 1. And then there is another set which includes, which every element of it is the ways to perform task 2. And we will see in the combinatorics that the total number of ways to perform to achieve your objective is going to be the number of elements in task A in task 1 multiplied by number of elements in task 2. Actually, this is very basic fundamental principle of counting, and this is mostly, it is very commonsensical also. But you will see that the set theory is the base for all of those. Even in computer science, in the subjects of theory of computation, entire theory of computation is a set membership problem. When I will start theory of computation, you will see that a language is a set of strings, and the whole of theory of computation almost is nothing but you are given a word, and you have to find out whether this word belongs to the language or not. What it really means is that whether this word is an element of this language, where language is a set. So in combinatorics is built upon set theory. In your theory of computation, because set is very fundamental. Set is just a collection of distinct elements. Like I've given you many examples. Everywhere where you find a distinct elements, and you are not and their order is not your concern, that oh, which element should be kept first, which element should be kept second, in what order is not a factor. Then all of then the collection of such distinct element is a set. So a set is a unordered unordered collection of distinct elements. Unordered collection of distinct elements. Distinct elements. When I was working in an office, I used to work on Java, and there was a interface or parent class called as collection. There's something to do with sets. So even if you give the repeated values, when you call that class, which is basically a set, it will return the elements with unique values. Means even if you give the set values to be 1, 2, 3, 3, if you give, let's say, a is equal to 1, 2, 3, 3, 4, right? So even then, when you it will return a to b, it will always return a to b 1, 2, and 3, 1, 2, 3, and 4. So even if any element is coming more than once in set, we are only dealing with distinct elements. So duplicates are not allowed. Duplicates are just ignored. Okay. So cardinality of A. What is cardinality of a set? Cardinality of the set is number of elements in the set. So cardinality of A is cardinality is represented like this. So this means cardinality of the set, which is equal to number of elements in the set. So cardinality of A is 4. Okay, cardinality of A is 4. And what are the elements of A? 1 is an element, 1 belongs to A, 2 belongs to A, 3 belongs to A, and 4 belongs to A. So because these are 4 elements, so cardinality is 4. Okay. So let's take only 1, 2, 3, 4. Let's take 1, 2, 3. Set is an unordered collection. Unordered collection. So we are just concerned with this distinct elements. So any other set, let's say if I take another set, any set with the same elements, 1, 2, 3 only, B is 3, 2, 1, and any other set C is 2, 1, and 3. Then all of these are equal sets mutually. A is equal to B, A is equal to C, B is equal to C, B is equal to A. So I was talking about that class in Java, which is a set. So what happens is every time that you call a set, it will return the elements, same elements, but their order may not be same. Every time the set is called, then what it returns is a set with same elements, but the order can be changed because order is irrelevant. We are not concerned with the order in which we are collecting the elements, like what element is to be collected first, or what is second element, what is third element. So instead, we don't talk like that. That what is the first element of a set, what is the second element of a set. It's just what are the elements of set. This is not an array. Array is an ordered collection of okay, later on, but array is an ordered collection of similar data types. Leave it. So all of these elements are same. A is equal to B. This is about the equality of two sets. Two sets are equal if their elements are same. If they have same elements, then both sets are equal. What is a subset of a set? What is a subset? So we are concerned with set A right now. So what is a subset of set A? If there is any other set whose elements are from set A, what does it mean? It means that a set B is said to be a subset of set A. A set B is said to be a subset of set A if all the elements of B is also an element of A. Is also an element of A. So take two sets. B is equal to 2, 3, and C is equal to 3, 5. Now, out of these two sets, B is the subset of A, but C is not a subset of A. B is a subset of A, and C is not a subset. C is not a subset of A. Why? Because all the elements of B, which is 2 and 3, all of the elements of B is also in A, or the elements of B are from set A only. But elements of C are not from set A alone, because C contains 5, which is not an element of A. So 5 belongs to C. This is the symbol to represent. So on this side, this is the element. Okay, and this is your set. So belong symbol means that this element belongs to this set, or this is the element of this set. So 5 belongs to C. Okay. But 5 does not belongs to A. So there is at least one element in C that is not from A. So C is not a subset of A. Okay. If a set is given to you and you are asked to form a subset from this set, so you know that the elements for a subset has to come from A only. Has to come from A only. And from the definition of a subset, the set A is a subset of itself. From the definition of subset, if all the elements of B, if all the elements of B is also an element of A, so definitely all the elements of A is an element of A. So every set is a subset of itself. Every set is a subset of itself. So every set is a subset of itself. Now, how do you form a subset? If a set is given to you, like A is given to me, and if I have to form a subset of A, how can I do that? So it is clear that the elements of that subset is going to come from A only. Is going to come from A only. So how can we form a subset? For every element, I have two choices. That in my subset, whether I will include this element or not. I may in my subset, I may include one or I may not include one. Okay, let's say I don't include one, but I include 2 and 3. Then this is what that subset is. So you can say that B is formed. How B is formed? Because I had two choices for every element. If I choose all of the element, then I get the set itself. And that is what it is. Every set is a subset of itself. I don't choose one. Every element has two choices. So for one, I am not choosing it to be a part of my subset. But other elements, 2 and 3, is a part of my subset. So B is a set which happens to be a subset of A. So let me write all possible subsets of A. So elements of A is 1, 2, 3. Okay. Now I know one of the subset is the set itself, and that is when we choose all of the element to be an element in my subset. If I choose every element of A to be an element of my subset, then what we get is this set 1, 2, and 3, and this is nothing but the set itself. So this is one of the subset. This is trivial subset. one of the trivial subset of a set is the set itself. That is when we choose every element to be in my subset, to be an element in my subset. Now, let me choose the elements, let me choose the subsets of cardinality 2. So the cardinality of the subset is going to be from 0 to 3. The length, the cardinality of A is 3. And my subset, the elements of my subset can be from set A only. So the maximum length of my subset will be 3. That is when the subset is the set itself. And for any other subset, what I'm going to do, either I'm going to pick 2 elements and not pick 1 element, or I'm going to pick 1 element or not pick 2 elements, or I'm going to not pick any of the element, because for every element I have 2 choices. So let me write possible subsets of cardinality 2. So for cardinality 2, for every combination, so if for every combination I am getting 1 subset, so let's say for cardinality 2 I have to select 2 elements in my set. I have to select 2 elements in my set, right? Let's say I don't select 1. If I don't select 1, and then I will select 2 and 3, and this set is 2, 3. Similarly, one another possibility is that I don't select 2. If I don't select 2, then my set, I get another subset which is 1 and 3. So as you can see, to form a subset, for every element of A, you have 2 choices. Either this element is in your subset or this element is not in your subset. And because of this, you are getting different combination. In this combination, all 1, 2, 3 is in your subset. In this combination, 1 is not in your subset, 2 and 3 is in your subset. So in this way, how many combinations you will get? This is very much like 1, 2, 3 is very much like Boolean table with 3 Boolean variables, and every variable can take value 0 or 1. So number of combinations possible is going to be 2 power 3. So here it is number of subsets possible for this set A is going to be 2 to the power 3. This time I will choose 1 and 2 and I will not choose 3. So my subset is 1 and 2. So these are all the subsets of cardinality 2. Now I will choose all possible subsets of cardinality 1. How can we do that? So for 2 elements I'm not going to make it a part of my subset, and for 1 element I'm going to put it in my subset. So in how many ways can you make the cardinality 1? So every time I'm just going to select 1. So let me select 1, then 2 and 3 I'm not selecting. I'm not selecting it to be my to be an element in my subset. So this is my subset. Then I'm selecting 2. Then I'm selecting 3. Now there is one more type of set. Okay, I've not discussed the types of sets, but there's one type of set which is called as empty set. Empty set is okay. How a set is represented? A set is represented by curly braces with elements, with all the elements separated by commas. So the elements of A is 1, 2, and 3. So it is enclosed between the elements of the set is enclosed between 2 curly braces, and they are separated by commas. So if a set does not have any element, then you write it like this. What does it mean? That this is a set. No doubt this is a set, but it has no element. Okay, that's what a empty set is. A set, it is a set, but no element. And it is also it is also represented as phi. So what phi is? Phi is equal to empty set. So one of the possible combination is that you don't select any of the element to be in your subset. So, and that is your phi, or this. So total number of subsets of set A is 8. There are 8 total subsets. These two, this and this, they are called trivial subsets. For every set, the set itself and the empty set, they are the trivial subsets of a set. Empty set is a subset of any set. Okay. For any given set, the set and the empty set, these two are trivial subsets of a set. Trivial subset. And remaining, so these two are trivial and remaining are subsets. One more thing, there is something called as proper subset. So what is a proper subset? Proper subset is a subset of set that is not the set itself. Or in a proper subset, you have the cardinality of proper subset has to be less than the cardinality of the set, or there is at least one element, and this is the real definition. A proper set subset of a set is when there is at least one element in the set which is not there in subset. So apart from this, for every other subset, there you can find at least one element which is in A but not in the subset. Like for this example, 1 is not a part of this subset, or 2 is not for this subset, 3 is not in this subset, 2 and 3 is not present in this subset, 1 and 3 is not present in this subset, 1 and 2 is not present in this subset. None of the element is present in this subset. So all of these subsets are proper subset. And for proper subset, how do we represent proper subset? For example, let's say this is my set B. B is equal to 2 and 3. Then how do I represent that this is a proper subset? The symbol for proper subset is this, so that B is a proper subset of A. Okay, so it is also a subset, so you can write, let's say if this is C, then you can write C is a subset of A, but C is also a subset of A. This is true also, and this is true also. Okay, but in this case, this is only a subset of A. This is only a subset of A. This 1, 2, 3, this is not a proper subset. This is not a proper subset, but this is a subset. Okay, so as you can see that for a given set of length 3, the total number of subsets possible is 8. If the size of the set is n, if the cardinality of the set is n, then what is the total number of subsets possible? It is going to be 2 to the power n, because then how many combinations are possible? 2 to the power n. Okay. So if the cardinality of A is n, the number of possible subsets of A, is equal to 2 to the power n. What is power set of A? What is a power set of A? Power set is a set of all the subsets of A. All the subsets of A. So what is the power set of A? Power set of A is going to be equal to all of this. Means power set of A, in the power set, each element is a set. So set can have a set as an element. So it is possible. It means, of course, just it has to be distinct element. Set can have anything as its element, anything. So not numbers, like in the introductory video. Student 1 is a set, can be one element. Student 2 can be another element in a set of the students. What is the power set of A? Power set of A is 1, 2, 3. 2 3, 1 3, 1 2, 1 2 3 and 5. So this set is a power set of A. So if the cardinality of A is n, then what is the cardinality of power set of A? If cardinality of A is n, then what is the cardinality of the power set of A? This is equal to 2 to the power n, because there are 2 to the power n elements. There are 2 to the power n subsets of a set. So each subset is an element of power set. So the cardinality of power set is 2 to the power n. This is trivial subset. This is trivial subset. Now you can say that this is one of the representation of set. This is how one of the way to represent a set is you have a curly braces and that encompasses all the elements which are separated by commas. There's another representation of set. You can represent set using a statement of English language that is called set builder notation. So that statement itself encompasses all the elements, all the possible elements. How? For example, in this case, A is equal to 1 2 3. I can write in English statement something like A is equal to X such that X belongs to natural number and X is less than 4. Then this is nothing but this. This n is also a set of natural numbers. N is set of natural numbers. So this is the example where number of elements is 3. But there are the sets can be finite set or it can be an infinite set. Some of the very popular infinite set, one of them is natural number, set of natural number. So which is n is set of natural numbers. Similarly, z set of all integers, q set of all rational numbers, r set of all real numbers. These are some of the popular infinite sets. Okay, what is the significance of set and subset? What is the significance of it? All of the subsets of this set A are nothing but set in themselves. They are the elements has to be decided from A. So it's like the world of A. So it is, in other way, you can understand this as that in the world of A, these are all possible sets that can be. In the world of A, this is the all possible sets that can be. For example, take the case of university. In university, you can have one set of students. Some students may be learning physics. Some students may have opt to learn chemistry. Some may have opt to learn mathematics. Some may have opt to learn about politics. Okay, so every set. So all the other sets, means the student who learn physics, they are going to be, the elements of these sets are going to be from the elements of set of students only. So set of students is like a universal set, and every other set in the context of university is a subset to this universal set. So likewise, in this case, A is a universal set. So universal set, A is a universal set, and every other set in the world of A, every other set is a subset to this A, because every other set, the elements will come from A only. Similarly, in case of university, for every other set, like physics students, set of chemistry students, set of politics students, set of English students, their elements are going to come from set of students only. Now, it might happen that, let's say, there is one subject where every student is learning that subject. For example, English literature. Everyone is learning that English language. Then, in this case, this subset is the set itself. Like this is the scenario of this, that that every set is a subset of itself. Similarly, there must be some subject where teachers just come to the classroom, but there is no one because nobody has opted to study that subject. Teachers just getting the salary, and the classroom is vacant. What can that subject be? What can that subject be? Let's say history. Let's say it's a college. College name is University of Science, but there is a history subject also, and there's also a history teacher in it. But nobody is interested in studying history. So in the set, so there is a set, that a set of history students or students of history. So there is a set, but there's no element in it. That is what is empty set is. Okay. So this is the significance of about set and subset. So what is a universal set? A universal set is a set that is a superset to every other set. So if for a given context, there is one universal set. Context of city population, what is the universal set? It's the set of all people in the city, and set of men, set of women. These are the subsets. So men or women, in these subsets, the element has to come from this universal set, which is the set of all people. So this is what it is. There's another representation of set. Right? I talked about this is one representation, curly braces, and inside of the curly braces you write every other element with a means separated by commas. The other notation is set builder notation, and there's another pictorial representation which is called as Venn diagram. In the next video, we will learn about set operations. So most of the set operations or the next video maybe will be properties of sets. All of them are very self-intuitive. Self-intuitive means you look at the property and you are like, obviously it has to be like that. And even for some properties where you don't get that obvious feeling, those properties can easily be visualized using Venn diagram. So maybe not in this video. In the next video, I will first start with Venn diagram, and then I will also cover set operations. Thank you very much. Venn diagram is also one of the ways that you can represent a set. Okay, it is a pictorial representation of set. For example, in this Venn diagram, universal set is represented by a rectangle. Okay, so this is your universal set. We have, I will draw 4 Venn diagrams in this video. So this is the universal set. It is represented by a rectangle. And any set other than the universal set, any arbitrary set is represented by enclosing curve. Preferably it is a circle. Maybe I won't be able to draw circle in some cases, but it's preferably a circle. So any arbitrary set using enclosing curve and all within the boundaries of the rectangle of universal set. For example, A is 1, 2, 3, 4, 5. So I'm going to draw like this. So this is A. This is a A. This is how A is represented. So all within the boundaries of the rectangle of universal set. So A is inside this rectangle. Likewise, any arbitrary set, it has to be inside the rectangle, because every set is a subset of universal set. Every set is a subset of universal set. If a set is a subset of some other set, it will be in your Venn diagram, it will be completely inside the superset. For example, in this case, C has 5, 8 and 9, D has 5, 8 and 9. So D is a subset to C. So let me draw C. C will have 3, 4, 5, 6, 7, 8, 9, 10. All of this will come under C. This is the set C. Now D is 5, 8, 9. So this is D. Okay, this is C, this is D. B is 3, 4, 5, 6, 7. So B must include 3, must include 4, must include 5, 6, and 7. So I draw B like this. This is my B. So B is inside universal set because B is a subset to universal set, and A and B, it's not like any of them is a subset of one another. They have some elements in common and some elements that is exclusive to A and some elements that is exclusive to B. 1 and 2 is exclusive to A, 1 and 2 is not present in B. Similarly, 6 and 7 is exclusive to B, 6 and 7 is not present in A. In this case, A is 1, 2, 3, 4, 5, and E is 8, 9, 10. 8, 9, 10. This is A and this is E. A is 1, 2, 3, 4, 5, and F is 3, 5, 2, 4, 1. So both have same elements. So this they are equal sets. A and F are equal sets. This is how you will represent A and F. Okay, both are equal sets. So their Venn diagram is just one circle, and this one circle represents both A and F both. So this is A and F both. I have taken four cases of two different sets. You can draw all of the sets A, B, C, D, E, F. You can draw all of the sets in one diagram also, but it would become very messy. That's why I have taken four cases separately. And these cases are, if you look at this, uh, none of the two sets, not neither A is a subset to B nor B is a subset to A. There are some elements in common, however, in this case. Similarly, in this case, if you can see, neither A is a subset to E nor E is a subset to A, but they don't have anything in common also. So they are. You can see here there is some part of this area. Within this area, there will be those elements that are common to A and B. But these two circles are completely separate. They do not intersect with one another. If there is nothing in common between A and E, there is nothing in common, then these type of two sets are called disjoint sets. So A and E are disjoint. A and E, A and E are disjoint sets. A and E are disjoint sets. In this case, D is a subset of C. A set is subset of another set, then it is going to be completely inside the superset. In this case, both are the same. Both are same. So there is only one circle, and this one circle represents both sets A and F. So A and F are equal. A and F are equal sets. For equal sets, there is one more way to look at it. We know that every set is a subset to itself, and if A and F are equal, it means that A is subset of F and F is subset of A. So, in order to show if the two sets are equal or not, then you can also use this thing. If A is a subset of F and F is a subset of A, if it goes both ways, that A is a subset of F and F is also a subset of A, it means they are equal. Then A and F are equal. A and F are equal. So this is about Venn diagram. Now in the next video, I will start set operations: union, intersection, set difference, symmetric difference, complement. Okay, thank you very much. Hi. Now we will look into different set operations like union, intersection, set difference, symmetric difference, and complement. Um, some of these operators are binary operators, except one, which is complement. Complement is a unary operator, means the operator that is going to be applied on a single set. But other operators like intersection operator or union operator or set difference or symmetric difference, they are binary because they are applied on two different sets. So you can think of it in this manner: op is your operator that can either be union or intersection or set difference or symmetric difference. So this op is an operation or operator that can be either union. This is a symbol for union. This is a symbol for intersection, union intersection. This is the symbol for set difference. This is a symbol for symmetric difference. Okay, and the two operands, the left operand and the right operand, they are going to be sets. So this is operand 1 and operand 2. So left operand 1 and operand 2. So op 1 and op 2, they are sets. Op 1 is a set and op 2 is also a set. They are sets. Operands is set and the operations are set operations. Set operations being applied to two sets. Now, what are these operations, different operations? That's what we are going to see one by one. Okay, let's start with intersection first. These are two sets, A and B. Okay, and intersection means that it will return a set that will have elements which belongs to this region. Means if you have set A and set B, the intersection of set A and set B means that you have all the elements that are in both A and B. So such that X not only belongs to A, but it has to belong to B also. Means that A intersection B, when you apply the intersection operation between two sets A and B, then this whole thing will give you a set, or this whole thing is a set. The set operation, when it is applied between two sets, the ultimate result is that of a set. So A intersection B is a set, and the elements of this set are the common elements of A and B. Okay, so A intersection B, the elements are elements of this set. Elements of this set are the common elements. The common elements of A and B. Common elements of A and B. Okay. For example, if A is, let's say, 1, 2, 3, 4, 5. And B is, let's say, 3, 5, 7, 9. Then what is the set A intersection B? A intersection B is a set, the elements of which are the common elements of A and B. What are the common elements between A and B? 3 is present in both sets. 3 is an element in both sets. 5 is an element in both sets. So A intersection B is 3 and 5. 3 and 5. If you just see any arbitrary two sets, this is how you represent two arbitrary sets. And all of these different set operations, whether it's intersection or union or set difference or XOR, symmetric difference, all of these different set operations are actually giving you some region from the Venn diagram. Just look at this. Okay, I will show union here. So let me just draw an arbitrary two sets here. So you can see how many different regions, because of these two sets, how many different regions are possible. One of the possible region is this region, which is the common portion. And for to get this element, all these elements, you have intersection operation. So your intersection operation will return a set that has all the elements in this region. Okay. Similarly, all other set operations will give you some of the region from this diagram. The union operation, which is the second operation that we will study. So second operation is union operation. So union operation will return you what area of the means elements from which region, everything. Uh, Intersection gives you this portion, right? Intersection gives you this portion, the common region. Union will give you all the elements that is in A or it is in B. It will just return everything. Okay, so what is a union? A union B. A union B. This is equal to all the elements X such that X belongs to A or X belongs to B. So think of this. If your set A contains n elements and set B contains m elements, okay, and they happen to be disjoint sets, means there is no sharing area. Okay, let me draw a disjoint set. If the number of elements in A is equal to m and number of elements in B is equal to n, then what is the number of elements of A union B? A union B will have all of it. All of it. So the number of elements in A union B is equal to m plus n. This is in case of disjoint sets. In case the sets are not disjoint, which is this arbitrary sets we are taking, what will happen? Let me take one example and show you. Let's say A is 1, 2, 3, 4, 5, 6 and B is 5, 6, 7, 8. Okay, then what will be A union B? A union B means every element from A and B. So you can just directly write the elements of A and B. Of course, the order does not matter. So you can reshuffle if you want. But the elements are from A and B. But if you just straight away take the elements of A and straight away takes the elements of B, 5 and 6 are going to be written twice because they are common elements. So when you are listing all the elements of A, one time you will write 5 and 6, and when you are listing all the elements of B, second time you will write 5 and 6. So 5 and 6 will be written twice, okay, and duplicates are not allowed. So let's say you will write all the elements of A 1, 2, 3, 4, 5, 6, and then all the elements of B 5, 6, 7, 8. Of course, when you are writing your set in this manner, you will correct yourself. You are not going to write 5, 6 twice because duplicates are not allowed in sets. Means duplicates are ignored in sets. Okay, but you cannot say that the number of elements in A union B for this case, in case when the two sets have some elements in common, they are not disjoint sets. You cannot directly say that this is equal to this is equal to number of elements in A plus number of elements in B, because that will be wrong. You can write this. You can say this in case of disjoint sets, because in disjoint sets you saying this is akin to just listing elements of A and elements of B without taking care if any element is coming twice because of the common element. So this goes fine in case of disjoint sets because there is no common element. When you list all the elements of A, then when you list elements of B, no element is going to come twice because there is no shared elements. There is no common elements. So in this case, this does not hold actually. So in number of elements in A union B is how much? Is going to be 8. You can see for yourself, number of elements in A union B is 1, 2, 3, 8. This is equal to 8. But what is the number of element in A? 6. And what is the number of element in B? 4. So 6 plus 4 has to be 10. So the correct formula in case of A union B to find the cardinality of A union B set is number of element in A plus number of element in B. Then I am going to subtract number of elements in A intersection B. When you subtract it one time, so what happens? I want everything, right? A and B. I want everything. So while listing all the elements of A, you have included these elements. Okay. Now you want every element of B also. So far good. But now again you did this because these are elements of B also. So you are counting this twice. So because you are writing it twice, or when you are calculating the number of elements, you are counting it twice. That's why I have subtracted with A intersection. Number of elements in this region, I have subtracted that. So as to not count the same element, the common element twice. And this formula is called as inclusion-exclusion principle. This is principle of inclusion and exclusion. Inclusion-exclusion principle. So this is inclusion-exclusion principle. Now I told you about the Venn diagram. So in this Venn diagram, this is about two arbitrary sets. Any two arbitrary sets, that's how it is represented by two circles, and there's going to be one intersection part. But these are the Venn diagram for two sets which are disjoint. From the arbitrary sets, you will come to the solutions. From the arbitrary sets, you will come to the solution. Here also from the arbitrary sets, I come to this solution. This is a general result because in case of this disjoint sets, the number of elements in A intersection B will become 0. So this becomes this only. So this is a general result. Okay, holds for all times. So when it becomes disjoint, then this term is 0. So for a general result, to get a general result, you take two arbitrary to get to a general outcome, or so as to get to a general result, you use the arbitrary two sets in this manner, and not you don't take these special cases. Like this is one special case where A is a subset to B. These are the special cases. For these special cases, you just fit that special part. Like in this case, A is a subset of B. Then A union B is nothing but B. When A is a subset of B, then A union B is B. Then what is the number of element in A union B? It has to be number of element in B, right? See if this formula holds for that or not. The number of elements in A union B is equal to number of element in A. Okay, no problem. Plus number of element in B minus number of element in A intersection B. And number of element in A intersection B is the entire A. So this becomes number of element in A plus number of element in B minus number of element in A, which is nothing but number of element in B. That's why whenever if you want to come to a solution, Using Venn diagram, you use these two sets. This is how you will draw two arbitrary sets in Venn diagram. Every set operation will give you elements from some region. You know what intersection will give? You have seen that. What union will give? It will give every elements. Now A minus B, A minus B, it will give those part of A, those elements of A, it will give this region. Those elements of A apart from those elements which are common with B. So A minus B will give you A minus something. So you are not going to return all the elements of A. Some elements of A you are going to remove. If this is your operator, which is minus, and left operand is A, then A minus means that those elements of A are going to be removed that is present in this set, that is present in B. Okay. If this is your two arbitrary sets A and B, then A minus B is this portion. Similarly, what will be B minus A? This portion. Okay. So B minus A is equal to, from the set B, you don't want to include those elements that are in A. So from the set B, from this whole set B, you don't want to include this part. So X such that X belongs to B, and X does not belongs to A. This is your set difference. Next is symmetric difference. Thank you. Now let's look at symmetric difference. So this set operation, symmetric difference, which is represented like this between two sets, A symmetric difference B. That's how we represent. This is the symbol for symmetric difference. And this set operation gives me what region? Gives me the elements of A and B that are not common. So this gives me those elements of A and B which is not in the intersection region. That is the elements of A that does not belong to B and elements of B that does not belong to A. This will give me a set that has element X belongs to A and X does not belongs to B, or X belongs to does not belongs to A and X belongs to B. Okay, so this is what your symmetric difference is. For example, if I take an example for A is equal to, let's say, 1, 2, 3, 4, 5, 6, 7, and B is equal to 5, 6, 7, 8, 9, and 10. Then what would be the elements in A or B? Elements in A or B will be everything apart from 5, 6, 7, because 5, 6, 7 is the intersection region. 5, 6, 7 are the common elements. So every element other than 5, 6, 7 will be a part of this A or B. For 1, 2, 3, 4, these conditions are fulfilled. So they will be a part of A or B. 1, 2, 3, 4. 5, 6, and 7 are common elements. So they will not be an element in A or B. 8, 9, 10. 8, 9, 10 fulfills this condition that they don't belong to A but they belong to B. So 8, 9 and 10. So this is what your symmetric difference is. Last set operation is, if you look at this complement set operation, then complement is a unary set operation. A complement is equal to all the elements x such that x does not belongs to A. X such that x does not belongs to A. So clearly, what is this element then? It means that A complement is equal to universal set minus A. Right? So A complement is all of this region. All of this region. Apart from A, everything. That is your A complement. All of this, every element in this region is A complement. Is an element in A complement. Now that you know all of these set operations, their fundamental definitions, now you can derive many formulas. So when you know the definitions and you have the Venn diagram, then you can form different equalities. What I mean to say is this. Look at this diagram. It is clear what is this shaded region. This shaded region is B minus A. This is one set. This is one set. So if I write equal to and write something here, then this has to be a set, and this has to be a set that is equal to this set. Means on both sides, if I, let's say, if I B minus A, if I write it as S1, set 1, then I may have different expression of set operations, but ultimately ultimately it will evaluate to one set, and let that set be S2. And if there is equal sign in it, then it means that the elements in S1 and elements in S2 are same. Okay, you can equate B minus A with respect to other set operations. How? For example, look at this. This is your region that you want. This is your region that you want. Can I not say that from the set B, I want to remove this region? From the set B, I want to remove this region. So I can say that B minus A is equal to B minus A intersection B. Will I be wrong to say that? No, because this region is nothing but B intersection B. So these two sets are equal. S1 and S2 are equal. So from the Venn diagram, you can write a lot of different expressions which will evaluate to the set which is equal to S1 or which is equal to B minus A. What other way can you write this? You can write B minus A. You can write B minus A to be equal to, because you just have to remove this part. If you want to remove this part, B minus A is equal to B intersection A complement, B intersection A complement, because A complement means apart from A, so you will have everything apart from A, but A complement will not include this region. So the common elements is just this. So you know what, from Venn diagram you can write these equations. Okay, and there's another way to prove this would be how you can prove it. When you have two sets and to prove the two sets that they are equal, if you have these two sets and you have to prove that whether this equation, okay, let's say this is the left hand side and this is the right hand side. So to prove the equality, you just have to show that LHS is equal to RHS. And in this case, what you have to show? You have to show that this set, which is S1, this set which is S1, that has to be equal to this set which is S2. You have to show that S1 is equal to S2. So how you will show it? using the fact that when two sets are equal, both are subset of one another. Like if S1 is subset of S2 and S2 is also a subset of S1, then S1 and S2 are equal. That's how you show it. Then how do we do that? We do that in this manner. Like if means I will take that for that X belongs to B minus A. I will take this that X belongs to B minus A. So what does it mean? It means that X belongs to A and X does not belongs to A. X belongs to B, X belongs to B and X does not belongs to A, right? And what does this mean? X belongs to B intersection A complement. What does it mean? It means that X belongs to B and X does not belongs to A. So both are same things. So they are equal. Okay, my plan was to cover this remaining two set operations and then move towards the laws of these what laws these different operations conform to and not conform to. And while explaining those laws, I would explain this, that when you have an equal sign, then you just have to show that the two sets are equal, and the way to show two sets are equal is one of the way is you can just visualize it using the Venn diagram, and which is an easy process. And the another way is to just go to the very fundamental level of what you know about definitions, and then just prove that both sets are equal. You can prove that how every element in this set is also an element in this, and how every element in this is also an element in this, which is to prove that the this set S1 is a subset of S2 and set S2 is a subset of S1. So I hope that if this part is not clear, then these two set operations are clear. So in the next video, I will explain different laws that these set operations satisfy or not satisfy. That video also I will deal with these things. So if things got messy a little bit here, because this was not in plan to go right away, but because I have made the video, I will keep it. Thank you very much. Now in this video, we will see different laws like commutative laws, distributive laws, associative laws, idempotent, identities, De Morgan's law. So one by one, we will see different laws as to what set operations obey those laws. For example, commutative laws, we will see that intersection, union, symmetric difference, they obey commutative laws. But set difference does not obey commutative laws. Similarly, intersection, union, and symmetric difference, they obey associative laws, but set difference does not. So we will look into what are these laws first. Means what is a commutative law? Commutative law is basically if you exchange or if you switch the operands, the left operand to be the right operand and right operand to be the left operand, even then the result is same given the operation. Let's say any operation is op is any operation, then there is a left operand op1 and there is a right operand op2. This op is said to be commutative if op1 op2 is equal to op2 op1. Okay. Now let's look into the intersection. B intersection A or A intersection B. From the Venn diagram, it is this region only. It's the same thing. Whether you do B intersection A or you do A intersection B, these are the elements that you are going to get in your set A intersection B or B intersection B. So A intersection B is equal to B intersection A, right? So what we get? We get that the intersection is commutative. Intersection operation is commutative. Now let's look at union. If you perform A union B, then you are getting all of these elements. Or you perform B union A, then you are getting all of these elements only. Union operation is commutative. Union operation is commutative. Now look at a symmetric difference. If you are doing A symmetric difference B, then these are the elements that you will get as a result of this operation. And the set B symmetric difference A also will have these elements only. So both sets are same. So the symmetric difference operation is commutative. So symmetric difference is commutative. Set difference. A minus B will give you this element. These elements. This is A minus B. A minus B. And B minus A will give you these elements. This is B minus A. So definitely these two sets are not same. A minus B and B minus A are not same. So set difference is not commutative. Set difference is not commutative. There's another law that involves three sets, which is associative law. You have three operands, and then you have this operation, any operation op. That is to be performed between two sets because op is a binary operation. This is one of the way you can do, right? This is one of the way you can perform the sequence of op operations when three operands are there. This is called left associative. This is left associative. Okay. The another possible way to perform this operation when you have three operands and a binary operator, we say that the operation op, this op operation is associative if the results because of left associative and the result because of right associative are equal. Means that if the set that you get by series of ops because of the left associative way or the result that you get by series of op operations because of the right associative way, if they are equal, that is said to be this op operation, it holds associative law. Intersection holds associative law, union holds associative law, set symmetric difference holds associative law, but set difference does not hold associative law. And if you look at this, these are the three sets A, B, and C. So just as this is the way to represent two arbitrary sets, this is the way to represent three arbitrary sets. Okay, three arbitrary sets in Venn diagram is represented using this figure. So now let's look into how the associative laws plays out in each of these set operations. On this side, I am doing A intersection B. First, perform this, and with the result of it, perform intersection with C. In this side, A intersection B. First, perform B intersection C, and then perform A intersection whatever the result is. So A intersection B is all of this area, right? All of this area is A intersection B. And then intersection C is only this part. In a similar way, when you do this, then B intersection C is all of this area. And A intersection B intersection C is just this part. Okay. So intersection operation is commutative and intersection operation is associative. So intersection operation is commutative and associative. Union operation. Left associative, A union B union C, and here right associative, A union B union C. Both ways it will give every element counted once. The result of all is all elements counted once. So left associative is equal to right associative. So union operation is commutative and associative. A symmetric difference B is equal to B symmetric difference A. Now we will look at the associative part. A associative B, left associative, symmetric difference C, and A symmetric difference B symmetric difference C. Now let's look at the left associative first. A symmetric difference B means all of this. Okay, all of this. Now this is the result of, means the shaded region is the result of this. Again, symmetric difference with C. So symmetric difference with C, which will remove these elements because these are the common part. So it will remove these elements. And now this is the result of this whole, means the set, because of this whole, means this whole series, this whole series of symmetric difference operations will give you a set that has these elements. What about this? B symmetric difference C. Will B and C will include these elements. B and C will include these elements. No. One more. This is what B and C will include. And then the result of it, symmetric difference with A, will remove this and this. And these portions will be added. Okay? Because these two portions will come as a common element with A. So we don't want common elements. We want the elements that are exclusive, elements that are exclusive to A but not present in this whole set. And for this set, we want the elements that belongs to this set but not belongs to it. So this is it. If you see, both are the same, both are returning same set of elements. So left associative and right associative, they are same. So symmetric difference is commutative and associative. In this video, I have used Venn diagram to show as a proof. Okay, but you can go for very fundamental, means this way. This is a simple by definition. You can go to prove on whether this is equal to this or not. And it is very simple, you write A intersection B, this is the definition, and B intersection A, this is the definition. So both are equal. And similarly, when you do A union B, this is what A union B is. And for B union A again, this is what B union A is. So both are same. A union B union C is A union B means X such that X belongs to A and X belongs to B. And union C, union X belongs to C. So it will become and X belongs to C, and similarly for this part. So for this it is very very obvious. You just have to directly, for both sides it's directly the same. Okay, one more thing is remaining as to how set difference is not associative. Like set difference is not commutative and it is not associative also. So A minus B is this region. A, this is B, this is C. A minus B is this region. And then minus C is just remove this part. And A minus B minus C will be, this is A, B and C. Then B minus C is this region. B minus C is this region. And A minus B minus C will be, so A minus B minus C will be, A will completely come. So we know that a union of sets A union B is equal to X such that X belongs to A or X belongs to B. So it can be if all the elements that is in A and all the elements that is in B. So A union B consists of all those elements that is in A and that is in B. And that's how we represent it. Or so if X belongs to A, then also it belongs to A union B. Means if X belongs to A, then also it belongs to A union B. Or if X belongs to B, then also it belongs to A union B. As you can see, for any element X, if that happens to be this element or this element or this element, then it belongs to A. It may happen to be here, it may happen to be here. So all of these elements, they belongs to A. And if they belongs to A, then they belongs to A union B. Because clearly A union B is A, superset to A. So A is a subset to A union B. A is a subset to A union B. Similarly, B is a subset to A union B. B is a subset to A union B. So this is one of the set operation, which is A union B. So in this set operation, to the set A, in your resultant set, what is happening is that to the set A, you are adding some other elements of another set, which is B. So you are adding the elements of another set, which is B. That is what A union B is. Similarly, B union A, we know that union is commutative. So in B union A, to the set B, you are adding the element of A also, and the resultant set is your B union A. Now let's look at intersection. The intersection of two sets, which is A intersection B. This is X such that X belongs to A and it also has to belong to B. Let's say this is X. Then X, does it belongs to A? Yes, this is true. X belongs to A is true. But X does it belongs to A intersection B? No. So X belongs to A, but X does not belongs to A intersection B. So in union, if X belongs to A, it means it belongs to A union B. But that's not the case with intersection. Of course, because the intersection region is this one. This is your intersection region. This is your intersection region. What if you have here Y? Then Y belongs to B. But Y does not belongs to A intersection B. But any element X, let's say here I am taking it to be Z. There's one arbitrary, any element in this region, Z. Or for every element Z that is in this region. So for every Z that belongs to A intersection B. If Z belongs to A intersection B, then Z belongs to A. Yes, of course. And Z belongs to B. You know, this is the way to prove this is the way to prove any set is a subset to other set. What is it? You take any for all element that belongs to this set. Okay, if you want to prove that a set A is a subset of B, then how do you prove it? You prove it by taking any element in A, and then you show that that element is also belongs to B. So you take, let's say X belongs to A, and with multiple step of inferences, you have to show that it ultimately shows X belongs to B. So if for every element of A it also belongs to B, then A is a subset of B. This is one of the way to show if any set is a subset. So here also, if you can see, I am just taking any element Z in that region. So for any general element Z, so any Z that belongs to A intersection B, or all Z that belongs to A intersection B, then it belongs to A also and it belongs to B also. It means that A intersection B is a subset of A and A intersection B is a subset of B. I have both ways of showing in this board right now. So on one side you have Venn diagram, on the other side you have this approach. If there was no Venn diagram also, then in this inference is enough to tell you that okay, A intersection B is a subset of A and A intersection B is a subset of B. Likewise in the union case, A is a subset of A union B and B is a subset of A union B. So these are the two ways to deal with set problems. You can either look from the Venn diagram, which is pictorial representation, and this will give you very easy. You know, I have already told you that using Venn diagram it is like, oh, it's obvious. And this is also another method because this is inference method. Even this, it means this, it means this. Oh, it means this. Okay, so what we can say from this is that A intersection B is a subset of A and A intersection B is a subset of B. Now let's look at complement. A complement is equal to X such that X does not belongs to A. This is my complement. X such that X does not belong to A. So take any element here. Let's say this element is any element X that is in A. So if X belongs to A, clearly X belongs to A. So X belongs to A means what? This is your A complement, right? Everything apart from A, anything outside of A. So if X belongs to A, then X does not belongs to A complement. Okay, and for any element Y that belongs to A complement region, so Y belongs to A complement, then Y does not belongs to A, right? So A and A complement, they are not subset of any of one another, because for any X that you are taking, that X does not belongs to the other way. But there is no intersection region also, because if for every X that belongs to A, you do not find any X that also belongs to A complement. For all X that belongs to A, that X belongs to, that X does not belongs to A complement. And for all Y that belongs to A complement, that Y does not belongs to A. So A and A complement are disjoint. So A and A complement are disjoint. A and A complement are disjoint. So we have seen that if for two given sets, if we have to show that this set is a subset of the other set, let's say there is set A and set B, and you want to show or you want to check whether set A is a subset of set B, then how do you do that? Is you take any element X that belongs to, you just do this, that X belongs to A. Okay, and because of means this is given now, and from it you can make many inferences, and if you get that X belongs to B, then it means that A is a subset of B, because this X is any element of X, because you are not taking a particular element in X, you are taking any X in A, any X in A. Then for any X in A, if you are getting that X to be in B, it means it applies for all elements, right? So in a similar manner, if using this process, if you get that X does not belongs to B, it means that A and B has no elements in common, right? So A and A complement are disjoint, and this A and A complement are disjoint in a manner that they are partition. This is a new term, partition. What is a partition? Partition of universal set. So a set and its complement partitions the universal set. A and A complement are disjoint. A set and its complement partitions the universal set. Partitions the universal set. What is a partition to a set? If you are dividing the set into multiple sets such that all of those sets, the union of all those sets will give you the set itself, but they all are mutually disjoint. If you take two arbitrary sets, This is A and this is B. Okay, you know what is A union B is. You know what is A union B is. But let's say I divide this A union B into regions. Into regions like this region. This region is 1. This region is 2. And this region is 3. Okay. So this 1 and 2 are mutually disjoint. There is no elements in common. And 2 and 3 are mutually disjoint. There are no elements in common. And 1 and 3 are mutually disjoint. What I mean is this. This is one region. This is region 1. This is region 2. Okay. This is region 3. So they are mutually disjoint region, and 1 union 2 union 3 is nothing but A union B. 1 union 2 union 3 is A union B. So what we say is that 1, 2 and 3, they are partitions of A union B. Similarly, any set with its complement is a partition of universal set. So a set and its complement partitions the universal set, means that A union A complement is equal to universal. So if you are given an expression that involves many set operations, like for example, expression can be something like this: A union B intersection B union A. Actually, this will give you nothing but A union B, right? So, but this is one expression in which you have different set operations, and some set of operations, the precedence will be that first you compute this, then you compute this, and then you perform the intersection between the two, because these are the braces. Braces have higher precedence. Similarly, some other set operations like A intersection B union C. So one method of getting to the solution is Venn diagram. The another method is that you start with this, that okay, if this is the set given, then you start with, okay, X belongs to A intersection B union C. Then you can make some conclusions from it. It must belongs to A, and it must belongs to B union C, because that's the definition of intersection. You know that. Okay, let me write the definitions, all of the definitions at one place. So then we can look at different expressions, and we can directly, as a cheat code, we will look at what is the inference because of union, and because of intersection, what is the inference because of union. So this is what you know. So from here you can get that X belongs to A, and so first point is X belongs to A, you know that. X also has to belong to B union C. Now B union C means that X belongs to B or X belongs to C. So this is your first jump from this set. This is your first inference. Now from this is your second inference. From here now this is your third inference. Okay. So this is one part, that X belongs to A, and this is second part, that it does not only have to belong to A for X to belong to this. It also has to belong to either B or C. Let me write all of the formal definitions of union intersection in this format. Hello. The actual video starts a little later. Actually, I saw the video and I think that there is something that I have to make clear. And that's why I am recording it and I will inject this part in the beginning of the video. So video will start after some time. Look, this is A union B complement. Okay, in this video I have talked about the De Morgan's law, absorption law, and there is something that I want to, make it clear. A union B complement. X belongs to A union B complement. Okay, this is your first jump. This implies that X uh, does not belongs to A union B, and this means that X does not belongs to A and X does not belongs to B. If X does not belongs to A union B, this means that it does not even belong to A or it does not even belong to B. What is this is nothing but X belongs to A complement and X belongs to B complement, and then this means that X belongs to A complement intersection B complement. Okay, now from here X belongs to A union B complement. Here X is any arbitrary X, so any X that belongs to A union B complement, that X also belongs to A intersection, sorry, A complement intersection B complement. Okay, so every element of A union B complement is also an element of A intersection B complement. So this means that A union B complement is a subset of A intersection A complement intersection B complement. Okay, actually we will see that they are equal. And how to show two sets are equal? By showing that this set is also a subset to this. Okay, now in the video what happens is I have directly, after doing this, I have directly said that these two are equal, but that is justified in the video because in the video I also have a Venn diagram alongside this. So whatever expression that comes out to be, there was a Venn diagram to verify it. So in the video it was justified, but I thought that maybe it gives the wrong impression that directly from here to, if you jump from here to here, it means they are equal. That's why I thought that it is to, I have to make it clear. So now I'm going to prove that this is also a subset to this, and that's why both are equal. So let's take A complement intersection B complement, then X belongs to A complement intersection B complement. This means that X belongs to A complement or X belongs to B complement. This means that X does not belongs to A or X does not belongs to B. This means that X does not belongs to A union B, which means that X belongs to A union B complement. So for any X that belongs to A complement intersection B complement, you are getting that X to also be belonging in this set. That's why what we will say is that A complement intersection B complement is a subset of A union B complement. And from looking at these two, we say that actually these are equal. So A union B complement, this set is nothing, is same as this set. Okay, now in the video this part was not done, so I have injected this video. I have made it separately, and I will inject this at the beginning of the video. Now, the video is length is about 40 minutes. Okay, so whenever ever, now it is upon you that whenever you see that if I have just gone from here to here and have directly said that these are equal, then there was also a Venn diagram to support this. Okay, number one point. And number 2 point is because I already know these results. That's why I forgot to. I knew that these two are same. This is a formula, De Morgan's law. So I knew it, and that's why I just did that in a haste. Now watch the video. Okay, in the last video we revisited union, intersection, and complement, and we saw that there are two ways to deal with properties of sets. To deal with equation involving set and set operations. One is Venn diagram, and the other is using the very obvious definitions of union and intersection, because those definitions are a kind of like a Boolean statement. For example, if I am saying that x belongs to A, then the value of it is either true or false, right? So anything like, for example, A union B is equal to, it is something like x belongs to A or x belongs to B. The value of this entity is either going to be true or false, and they are connected using a connective. So it is very much like think of it in case of propositional calculus, right? So in this video we will focus mostly, maybe Venn diagram also, but mostly into this approach, because this is a statement, like the statement that involves Boolean values. So there can be many inferences made from this statement, and then you get something, then you get something. So we will see that how to do this type of inferences. A union B, this is equal to x such that x belongs to A or x belongs to B, right? This is one set operation which is union. And the another set operation is intersection, which means that A intersection B, this is equal to x such that x belongs to A and x belongs to B. So, or just like in the propositional calculus, what is the or operation in propositional calculus? For a or statement to be true, any one operand has to be. So for an element to be a part of A union B, even if it belongs to A, then that is in A union B. If it belongs to B also, it is also in A union B. An element is given to you, let's say Y, and you have to this is called set membership problem also, that if an element is given to you, whether this element is a part of set or not. So if this element belongs to A union B is x belongs to A or x belongs to B. When you have this or statement here, you evaluate from left to right, and in the process, if you get true, you don't need to evaluate the rest of the steps. Y belongs to A or Y belongs to B. Let's say this is false. Then you cannot say whether Y belongs to A union B unless you check Y belongs to B or not. But if this was true, if Y belongs to A was true, then definitely Y belongs to A union B. In case of intersection, you have AND here. AND means, in AND operation, in propositional logic, AND operation means that the left side and the right side, um, left proposition and the right proposition, both has to be true for whole statement to be true. So A intersection B, as the name suggests, is about the common elements. So it has to belongs to A and it also has to belong to B. Complement. Complement means A complement. A complement means what? A complement means X does not belongs to A. Okay. And simple A set means that X does not belongs to A complement. That's why complement, they are partitioned to the universal set. We have seen this in the last video. In this video, what I am going to do is I am going to use different expressions and try to infer using this. So if I perform A union B, if I perform the complement to A union B, let me perform the complement to A union B, then what does it mean? A complement means X does not belongs to A. So A union B complement means what? X does not belongs to A union B. This is your first jump. Uh, what this means? From very basic definition, this means this. Okay. Now you know that if it does not belongs to A union B, what is A union B? A union B means it either belongs to A, or if it belongs to B, then I will include it in A union B. So if it is in A or if it is in B, I am going to include it in here. But I want those X that does not belongs to A union B, means I want these regions. I want these regions, right? The regions that does not belongs to A union B. So what does it mean? It means that X does not belongs to A and X does not belongs to B. Right? X does not belongs to A. X does not belongs to A means X belongs to A complement. And X does not belongs to B means X belongs to B complement. What does this mean? This means that X belongs to A intersection A complement intersection B complement. A intersection B is X belongs to A and X belongs to B. So X belongs to A dash and X belongs to B dash means X belongs to A dash intersection B dash. Right? Okay. Let's apply complement to intersection. A intersection B complement means that X does not belongs to A intersection B. Okay, what I basically mean, X is not in this region. X should not belongs to this region. Now, if this will become X does not belongs to A complement, or X does not belong, X belongs to A complement, or X belongs to B complement. A complement will take everything apart from A. So it may include B, but this region, which are exclusive to B. Okay, but A complement does not include this region, which has to be in it. So B complement includes those regions. Got it? So, and this is what your De Morgan's law is. If you remember in your from propositional calculus, I mean, I have uploaded 2 videos, maybe not in the whiteboard, but I mean, as of now. But I have uploaded almost 2 or 3 videos on propositional logic, which includes these basics, complement and operation and or operation. I hope so. So from there also, you in there in your propositional logic, what was your De Morgan's law? De Morgan's law was applied between or and, right? So in case of De Morgan's, if we remember, P1 or P2, or is like this, right? This is or P1 or P2 complement. This is nothing but P1 complement and P2 complement, right? So here it's almost the same thing. It's almost the same thing. Means, okay, how can you write this? Okay, so next step is nothing but if I have to just show it in terms of the operations, A complement or means union B complement, right? So I can say from here, from this I got this. So I can say that A union B complement is equal to nothing but A complement intersection B complement. And from here, A intersection B complement, this is equal to A complement union B complement. A complement union B complement. So you got this, right? So you know this is the De Morgan's law in propositional calculus. And what are you doing here? It's like you have not operation outside of P1 or P2. Then what happens because of this? To the propositions you perform the complement and or becomes and, right? Similar case is happening here. X does not belongs to A union B means, and A union B is what? A union B is what? X belongs to A or X belongs to B. So what is happening is that here the propositions is getting complemented. Here you are getting your set is getting complemented, right? X belongs to A complement, X belongs to B, so X belongs to B complement. And here the OR operation in your propositional calculus is getting into and here also this OR is becoming AND. So this is what complementation does. You can relate it from propositional logic. So in complementation, what happens is you just remember it. The set gets complemented, or union becomes intersection. Set gets complemented, and intersection becomes union. And that is your De Morgan's law. The name is same for both. In case of okay, if I do the De Morgan's law in the opposite manner, this is OR. So if P1 and P2 complement, this is equal to P1 complement. This is AND, so this is OR P2 complement. We have seen this in mathematical logic. So same thing is happening here also. You have A intersection B. So in place of propositions P1 and P2, you have two sets, A and B. So A intersection B complement. The result is set complement, A intersection. Intersection becomes union, set complement. So when you are performing this does not belongs to, then set gets complemented. When X does not belongs to something, then the set will get complemented here. First, I am complementing this OR into AND, but X does not belongs to A. I have written it here. Okay. X belongs to A complement means that X does not belongs to A. And X belongs to A means that X does not belongs to A complement. So X does not belongs to A means X does not belongs to A means X belongs to A complement. X does not belongs to B. X does not belongs to B means X belongs to B complement. So this is very simple actually. You have, okay, let me just summarize it. Okay, how many basic set operations are there? Union, Union is your basic set operations, intersection, and complement, right? You know the basic definition of union. It is that x belongs simple x belongs to a or x belongs to b. Basic definition of intersection is x belongs to a and x belongs to b. And when you are applying complement over any set expression, then what you will do, I mean, that is involving equal sign. Let's say you are doing complementing both sides, something like this. So whatever, if to a set expression you are applying complement, then what is the resultant expression directly you can get? How you can get it? You will just change this union into intersection and are set to complement. Okay, a or a complement, then a, and it is vice versa. Got it? So that's what you have to do. Okay, now we have two more, symmetric difference and set difference. So let's look at some of the properties of the symmetric and set difference also. Symmetric, just like we see that this union operation, this or operation, you can, the analogous in the mathematical logic is the or operation, and this and is nothing but and operation. So similarly, symmetric difference is nothing but like the XOR operation in the propositional logic. So A is symmetric difference B. What the basic definition of it is? It's like this: X belongs to A means I want exclusive part of A and B, right? Not the intersection part. Everything but except the intersection part. So if this is your A and this is your B, then apart from this intersection part, all of it is in A symmetric difference B. So it's like X belongs to A, but it may include elements from here also. So you have to add that, and X does not belongs to B. So this portion is covered. Or X belongs to B, but you have to make sure this part of B is not included. So and X does not belongs to A, right? This is your definition, direct definition. Now, what can you infer from this? What can you infer from this? X belongs to A and X does not belongs to B. Look at this part. X belongs to A and X does not belongs to B. This is A intersection B complement. X does not belongs to B means X does not belongs to B means that X belongs to B complement. So this part is A and B intersection B complement, right? Or means union. Or means union. Then look at this part. X belongs to B and so intersection. X belongs to B. B intersection. X does not belongs to A. X does not belongs to A means X belongs to A complement. So B A complement. So what do you get from here? You get that A symmetric difference B asymmetric difference B equal to A intersection B complement union B intersection A complement. I am just writing it in terms of set operations, and you can verify it very easily from means this and this is the same thing, and you can see clearly A intersection B complement is this region, B intersection A complement is this region. Let's do something. Let's do the complement of asymmetric difference B. Okay, so we have the Venn diagram here. So we know what the complement of A symmetric difference B should be. From the Venn diagram, you know, if this is your complete Venn diagram, including the universal set. Now let's perform A symmetric difference B union. Let's see what we will get. From the Venn diagram, tell me what should be the region? Tell me. Oh, asymmetric difference B का complement Venn diagram से देख के बताओ कि कहाँ होगा. So it should not include this region and it should not include this region. So apart from that, this belongs to the complement of this, and all of this also belongs to the complement. Right? So if when you perform a complement to this, means that you are complementing on both sides of the equation. Now you can just do the De Morgan's law, and whatever the result would be, that result would include these regions only. Okay, so there are two things you can think about this. Number one, you can perform De Morgan's law and come to the solution, and you have your Venn diagram in place to verify if your solution is matching or not. Or you can directly give the solution by looking at the Venn diagram. That okay, this means okay, just by looking at the Venn diagram, what should be the solution? I am just writing that solution. Where should I write? I'm just writing that solution here. Okay, just by looking at the Venn diagram, what should be the solution? So the solution should be this region is A intersection B. A intersection B union. What is this region? What is this region then? This region is clearly it belongs to A complement, but not this part. Means that A complement intersection B complement. Can I say that A complement intersection B complement? Because I don't have to include this region. So B complement will have everything, but it will include A also. The regions of A in it means regions of A which is exclusive to A and not B, not the common elements of A from B. So it B complement will include this also, but because I am doing intersection with A complement, so this is in the intersection region will be just this. Now let's take the De Morgan's law and see if we are arriving to this or not. One more thing, while I was writing directly from the Venn diagram, I thought of writing A complement. So A complement will include everything apart from A, but I wanted to subtract B from it. So I wanted to do something like this: A complement minus B complement. No, A complement minus B. I wanted to do this. If you see, there is no problem in this. If you write this also, this is also correct. Because it will from the set A complement, it will remove the elements of B only. It will remove those elements in from A complement, it will remove those elements that are also in B. So it both of them will give the same result only. But why I chose this something like this, because I am going to use the De Morgan's law, and De Morgan's law involves union, intersection, and complement. So let's apply the De Morgan's law here. So let's say this is C, and let's say this is D. then now this is nothing but C union B complement. So it is from De Morgan's law, C complement union का intersection D का complement. Now what is C? C is A intersection B complement. So A intersection B complement intersection D is nothing but B intersection A complement का complement. Now perform this. This is nothing but A complement intersection का union B complement का complement means B intersection B complement intersection का union A complement is A. This equation and this equation are just two ways of representing same regions. Let's see that A complement will include everything apart from A, but it will also include B. And B complement will include everything apart from B, and it will also include A. Okay, but then you are performing intersection, so this will include only this region. Got it? Means I got it, but it is messy, so I have to make a new Venn diagram to explain this. Let's take here. I don't know if it is visible or not. Let me draw a Venn diagram. Where should I draw? Let me draw a Venn diagram and show that whatever regions these are giving, same regions are given by this. So these two expressions are equal because the elements are same. This is your universal set. A complement is these region. These regions are A complement. Union B. So this part is from B. This is also included now. This is A complement union B. What is B complement union A? B complement is all of these regions. Okay, let me do it like this. B complement is these regions. And these also. Right? Now you are doing union A. So A is these elements from A are included. Now this is also included. To this you are performing intersection. So you are now going to exclude those regions which do not have both colors, green and orange. Intersection means it should include to both. So you have to remove these regions and these regions. So from De Morgan's law you got this, and when you can look at the Venn diagram, you are getting the right result. Okay, what about this? A intersection B include these region. Union A complement include all of this, but the region with B also. But then I am performing intersection with B complement. That it has to also come under B complement. So B complement, this B portion is gone. So it will only include all of this, right? So A intersection B complement will include these regions, all of these regions, and A intersection B include this region. So this expression and this expression are same. Let's say this is set C. This is set C, and set this whole expression is set D, then what I can say that C and D are equal sets. C and D are equal sets because they have same elements. Okay, thank you. Let's look at set difference now. A minus B. We know that what is this A minus B? This is X, those elements of A that are not in B. Means from the elements of A, you are removing those elements that are in B also. That's why X, this is A, this is B. From this set A, you are removing these elements, right? So this is your A minus B. As you can see very clearly that this you can write it as A intersection. This you can write it as A and intersection S does not belongs to B. B complement. A intersection B complement, which is this region. Okay. So A minus B is equal to A intersection B complement. In one of the previous videos, I have come to this using Venn diagram also, right? From the Venn diagram, it is also quite clear that this region is nothing but A intersection B complement. So this is the part. My hand waving should be clear, right? Now, just look at this. A intersection B complement. What we can say is asymmetric difference B. We can say that asymmetric difference B is also A intersection B complement union B intersection A complement. This is what we know. It means that asymmetric difference B is A minus B union B minus A. Right? Okay, I will do it again. Asymmetric difference B, I can write this as it is these regions and these regions, right? So asymmetric difference B is A intersection B complement union B intersection A complement. In the last video we have seen that we are trying to get the complement of A intersection B. This is the complement of A symmetric difference B. But the formula of asymmetric difference B is this only, that asymmetric difference B is equal to A intersection B complement union B intersection A complement. And A intersection B complement is nothing but A minus B. A intersection B complement is A minus B. So it is A minus B union B minus A. And as you can see, this is nothing but A minus B and this is B minus A and then union of it. So these are some of the properties. Now let's try to find the complement of A set difference B. Let's try to find this. Okay. So I will remove that part now. A minus B complement. What does this mean? it means that X does not belongs to A minus B, right? It means what? X belongs to A. It means that X does not belongs to A minus B. It means that X does not belongs to A minus B is X belongs to A, and X does not belongs to B. So what I would do is X belongs to means A. So A का complement करेंगे. Look at this. You are performing X does not belongs to this set. So you are in a way you are doing a complement on some operation. So here we will apply De Morgan's law now. So let me apply De Morgan's law. X belongs to A complement and becomes or X belongs to X does not belongs to B means X belongs to B. Means X belongs to A, so X belongs to X does not belongs to A. So that is X belongs to A complement. X does not belongs to B means X does not belongs to B complement means that X belongs to B. And this is nothing but A complement union B. Now let's see if this the region because in the Venn diagram because of this expression is this or not. Okay. So A minus B complement will include these regions. A minus B complement will include these regions, and these regions is nothing but A complement union B. A complement include everything, and because you are applying union B, then because of it these regions are also included in it. So this is true. So as you can see that what I'm saying is that you don't have to actually remember. You know, you can see there are many formulas. Uh, in any book, if you look at the books, there are many formulas, but all of them it is from the very basic definition you can get to it. You just have to master De Morgan's law. So union, intersection, and complementation, the basic definitions you know, and then if you know the De Morgan's law, then you can arrive at this from here only. Okay, like I am just applying De Morgan's law directly from in this manner. So this you can think of it. You can think of it in just in terms of set operations directly. How? What I am doing? A X belongs to A and X does not belongs to B. This is nothing but A intersection B complement directly. You can write it like this, and you are applying X does not belong to this means complement of it. Now from directly apply De Morgan's law. A complement union B. That's what it is. So I am writing it in this way, or you can change it here, and you can directly deal with set operations. It's the same thing. Okay, I think this is enough. It's very easy. If we here it is or, it means you will repeat, or it means union. Belongs to, directly you write the set. Belongs to B, directly you write the set. So let me just summarize what we have seen so far. The formulas that we have seen so far. Let me just summarize it. But we know how to get to the bottom line. These are the three very fundamental set operations. And then we know about set difference A minus B, and we found that A minus B is A intersection B complement, and A symmetric difference B is equal to A minus B union B minus A, which is equal to A minus B is A intersection B complement union B minus A is B intersection A complement. Now let's get into operations involving three sets. And involving three sets, we have looked at the associative property that set union intersection and set symmetric difference. They are associative, but set difference is not associative. Now there is something called as distributive law. Now let's do that. Let's see that. Now let's look at distributive laws. What are distributive laws? There are two. One is A intersection B union C. This is equal to A intersection B union A intersection C. So whatever is outside operation, whatever this is outside of it, it will be applied to the elements of inside it. So A intersection B, A intersection C, and they will be joined using a union. This is like distributing intersection. Okay. So or A union, when union is outside, then it is also distributive. So union will be distributive over the intersection of two sets. So it is like A union B and A union C, A union B, A union C connected by intersection. Now I have to show how these two sets are same sets. How these two are the same sets. That's what I have to show. We know that to show two sets are same, we just have to show that both sets are equal. And to show two sets are equal, we just have to show that one set is the subset of the other and that other set is also a subset of this. So both are equal. This is one of the way to show. So let's say this is my first and this is my second. This whole expression, whatever the resultant set is, and the resultant set of this equation, this expression, both are same sets. Means if this is let's say S1 and this is S2, I just have to show that S1 is equal to S2. So let's take one by one. You can show it using Venn diagram. Let me use Venn diagram because we have been using the arbitrary two sets in a Venn diagram. This is a very good opportunity to use arbitrary three sets in a Venn diagram. So any three arbitrary sets is represented like this. Let's say this is A, this is B, and this is C. So as you can see, let me just analyze this figure. This is your set A, this is your set B, this is your set C. And look at the regions. This whole region are the elements that are common with A and B. This whole region contain those elements that are common to A and C, and this whole region contains the elements that are common to B and C. Only this region contains those elements that are common to A, that are common to B, and that are common to C. All three. Do is I am going to give it a number. Okay. So this one, mind it, this is a partition. Okay. So one means any two number are disjoint. Okay. So I am partitioning A union B union C. 1, 2, 3, 4, 5, 6, 7. So there is nothing in common between 1 and 6, 1 and 2, 1 and 4. Nothing in common. Nothing in common between any two numbered regions because we are partitioning it. You know, in a case of partition, the elements are disjoint. So if I am saying what is A, then you can say 1 union, 2 union, 6 union, 4. And what is the number of elements in A? The number of elements in 1 plus number of elements in 2, number of elements in 6, number of elements in 4. No problem, right? So A is 1 union 2 union 6 union 4, and B is 2 union 3 union 4 union 5. C is 4 union 5 union 6 union 7. Now B union C means what? B union C means 2 union 3 union 4 union 5 union 6 union 7. So A intersection B union C is equal to A is 1 2 6 4. So 2 4 and 6. 2 union 4 union 6 means on the left side, what are the element, what are the regions? 2 4 and 6, these regions, right? Now let's look at the right side, that is S2. A intersection B is what? 2 and 4. So 2 union 4. And A intersection C is 1 4 4 and 6. 4 union 6. Union of these two. A intersection B union A intersection C. This is equal to 2 union 4 union 6. Both are same. So this holds, right? Now let's look at the second problem now. What is the left side? B intersection C. B intersection C is 4 and 5. B intersection C is 4 and 5. And A union B intersection C. A union B intersection C will be 1 2 6 4. So 2 4 6. So just one will be added, right? Now come to the second side, this side. A union B. A union B is 1 2 3 4 5 and 6. A union B is 1 union 2 union 1 2 3 4 5 6. 1 2 3 4 5 6. This is A union B. And A union C is A union C is A union C is 1 2 4 5 6 7. 1 union 2 union 4 union 5 union 6 union 7. And now perform the intersection. A union B intersection A union C. Then what is the intersection of it? Intersection 1 2 4 5 6. 1 union 2 union 4 union 5 union 6. Both sides not matching. 1 2 4 6. 5 is not here. So A union B union C. B intersection C. A union B intersection C, B intersection C is 4 and 5, so union 5 bhi hoga. So both are same things. So this is distributive law. Now, if you know the De Morgan's law and distributive law, then you can solve the set problems involving set expressions, because that's what you have to just do. That you have to look at, okay, in this manner you will just distribute it. If there's a complement over any expression, you know what to do. You just have to change the union into intersection, and you have to just complement the set. If it is already in the complemented form, then it will be just the set, right? So if you know distributive law, if you know De Morgan's law, then you will be able to solve all the problems. Now in the next video, we will look at some other laws like absorption law, maybe some other properties, which is basically set formulas. In this video, we will look at some more properties of sets and maybe complete Cartesian product of sets also. Let's look at some properties of sets involving the universal set and null set. When you perform union of any set with universal set, you will get the universal set itself. And when you perform the union of any set with a null set, you will get the set itself. Any set A union universal set is the universal set itself. So A union universal set is equal to universal set itself. And A union phi is equal to A. Okay. Now let's look at intersection. A intersection universal set is equal to, this is your A, this is your universal set. The common elements are A itself. So A intersection universal set is equal to A, and A intersection null element is null element because there's nothing in common. Okay, let's add some more set difference, symmetric difference. So let's say set difference. A minus universal set is equal to what? So from set A, you are removing those elements that are in universal set. So you are removing all the elements. So it becomes an empty set. A minus phi. You are not removing anything. So this is equal to A itself. A symmetric difference with universal set. A symmetric difference universal set and A symmetric difference phi. What is asymmetric difference universal set? Means that I want those elements that are exclusive to the set. Okay, means those elements of A that are not in universal set and those elements of universal set that are not in A. So of course all the elements of A is in universal set, but there are elements in the universal set that is not in A, which is A complement. So A symmetric difference universal set is equal to A complement. Asymmetric difference with phi means that you want those elements of A that are exclusive to A as well as those elements of phi which are exclusive to phi. Nothing in common means not including those elements that are common in A and phi. Phi has no element at all. So whatever is in A is exclusive to A. So this is equal to A. So union, intersection, set difference, symmetric difference. Any other set operations? Complement. Okay, let's look at complement. Complement is is a complement is not a binary operation. So what can I say? There's two things. One is A union A complement is equal to universal set. We know that because A and A complement partitions the universal set. A complement is equal to A. Okay. So that's it. These are the some different set operations involving universal set and universal set and null set. Some special names actually given, like for example, A union universal set is universal set. Okay, leave it. Look at these two right now. Oh, I will come to that, but look at these two right now. These two operations. A union phi is A. A intersection universal set is A. These two are called the identity laws. These two are identity laws. Identity laws. Identity laws, as in whatever your set is, that is what you are getting as a result. Okay. So you can say that the phi is a identity element of union operation. Means that to any set, if you apply the union with phi, you will get the set itself. So phi is a identity element of union operation. Similarly, universal set is a identity element for intersection operation. Any set, when it is performed the intersection operation with universal set, you will get the set itself. Of course, you know that union and intersection are commutative. So in these two cases, look at this. In these two cases, your set union with universal set, you get the universal set. Your set, any set intersection with phi, you get phi. So here you are not getting the set itself as the result, but you are getting this element. Means how U is a identity element. Similarly, this is, you can say, dominant element. So phi is a dominant element for intersection operation. So any set, when it is performed intersection with phi, then the result is phi. Any set, if you perform the union with universal set, the result is the universal set. So these are called domination laws. Look at this. Complement is A union A complement is universal set because A and A complement partitions itself. So it means, of course, they are disjoint. So I can write that A intersection A complement is phi. A union B intersection C. This is equal to what? Using distributive laws, we can say that this is nothing but A union B intersection A union C. This is by distributive law. Similarly, there is another distributive law which is A intersection B union C is equal to A intersection B union A intersection C. Right? So why I have again started distributive law? Because I want to describe absorption law. Actually, absorption laws is when any one of this set, B or C, is a set outside. Means if you have A union A intersection C, or here you can say, let's take C as A and A intersection B union A. So if under the bracket, if any one set is A, then the result is A. This is called as absorption loss. This is absorption loss. You can think why it is the case. It's very easy because A intersection C will have the common elements of A and C. So we'll have the elements from A, and A union some of the elements of A is the A itself. Similarly, A intersection. Now B union A will have all the elements of A and B, but after that, we want intersection only. So the elements, the exclusive portion of A of B, sorry, exclusive portion of B will get removed because of this intersection, and you will get A only. Okay, so these are absorption loss. I think I should end this video right now. There are other set operations. Maybe I will take another video for it. And then Cartesian product. Thank you very much. This is probably the last video covering the fundamentals of sets. In the next video, we will start with relations. Okay, so in this video, we will see once again the arbitrary two sets using Venn diagram and arbitrary three sets using Venn diagram, and how to just write some set formula just by looking at the Venn diagram. Okay, for example, you know what is A minus B? A minus B is this region. Means in context of set A and set B, those elements of A that are exclusive to A, means those elements of A that are just that belongs to A but does not belongs to B. So as you can see that this is a set A, and A minus. A minus means that from set A you are removing some elements. So what elements are you removing? The elements that are present in B. That's how we look at set difference. So this is the region for set difference, right? This is the region for set difference, A minus B. So how can you get this A minus B? One of the way we have seen that, which is this is nothing but A intersection. So if I am doing A intersection, then what should be here? So this is whole your A, then intersection, whatever you are going to write here, that has to include all of this, and that does should not have this area. So, and this is the thing but B complement, because B complement don't have this area, and it have all of these, no doubt, but it also have this. So the intersection region is nothing, is only your required shaded region. This is one thing. Or you can say A minus B is A, from A you want to remove some elements, right? A minus something. So from A you want to remove some elements of A which is in intersection with B. So A minus A intersection B is also can also be your one formula. So A minus B can also be A minus A intersection B. So from A you are removing those elements that are also in B or that are in common with B. Okay, intersection B. A intersection B is from A you want to remove those regions that are exclusive to A. You can say that this is A minus, from A you want to remove these regions. So these regions are A minus B. So it is A minus A minus B. A intersection B is A minus A minus B. Okay. A XOR B. You include all the elements from A and B which are not common elements. So you are including these regions and these regions. So this is A minus B union B minus A. Maybe we have visited these formulas before. I am just using this video to show how you can just look at Venn diagram and try to come up with a formula. We have not seen a lot about three arbitrary sets. I am using this video. The main purpose was to introduce the union between the three sets. Like we have seen A union B, right? We know what is A union B, but there is something about A union B union C that I want to cover in this video. That what is A union B union C? Because if you remember, in the union of two sets, uh, we we saw that the okay, from the arbitrary Venn diagram you come up with a inclusion exclusion principle, like number of elements in A union B is equal to number of element in A plus number of element in B minus number of element in A intersection B. This formula is called inclusion exclusion principle, because in just straight away writing all the elements of A and B, you will write the common region twice. That's why you will have to subtract the number of elements in A intersection B. And if the sets are disjoint, this number is nothing but zero. So this is a general formula that will encapsulate every situation. In a similar manner, now we will look at the that how what this formula will turn into if we don't have only two sets. Number of elements in A union B union C. That's what we will see in this video. Okay, I will erase this. Let's say if I write that the number of elements in A union B union C is equal to number of elements in A plus number of elements in B plus number of elements in C, then actually we are counting some elements twice, some elements as thrice. Let's see how. Look at this region. Look at this region. This region. When you straight away write the elements of A, you are including this region once, this area once. But when you are writing the elements of B, then this region is now counted twice. Okay, so you have to from this sum you have to remove minus number of elements in A intersection B, because these elements are counted twice. Similarly, uh, this region, this region, when you are listing all the elements of B and C, these elements are being counted twice, so you have to remove them one time. So it becomes minus number of elements in B intersection C. Similarly, if you look at this region, when you are writing the elements of A and then element of C, then these regions are being counted twice. So you have to remove them once. So number of elements in A intersection C. And then look at this region. If you look at this region is in the intersection of A also, in the intersection of B also, in the intersection of C also. And this region is being added every time. Means when you are adding A, when you are listing all the elements of A, then this region is added. When you are listing elements of B, then this region is added. And when you are listing elements of C, then this region is being added. So they are added three times. But when you are subtracting the intersection of A intersection B, then A intersection B not only includes only up to this region. A intersection B includes all of this. So because these are counted thrice, no doubt, but you are also while subtracting elements common in A and B, common in B and C, common in A and C, you have actually not included this region. So you have to add it. You have to add it plus number of elements in A intersection B intersection C, because no doubt it was added thrice, but because we have subtracted A intersection B the one time, the elements of A intersection, number of elements in A intersection B, you have subtracted Now in this video, let's look at the product of sets. So what is the product of two sets A and B? Let's say you have two sets a set A and a set B. Then what is A cross B? So we have seen different set operations like union, intersection, set difference, set symmetric difference between two sets. And the result of it is also a set. This is also one of the set operation. And the result of this set operation is also a set. Okay. A set is an unordered collection, but the result of it is also an unordered collection, but unordered collection of ordered pairs. So this is a very important point. So A cross B will give you set, no doubt set, which is an unordered collection. Unordered collection. So set of all possible ordered pairs. Set of all possible ordered pairs. Okay. So what do I mean by this ordered pairs? What is this ordered pair? Okay. Like let's say if A is 1, 2, and 3, and let's take B to be A, B, C. Then what is ordered pair? Means that this is equal to a set. This is a set which is each element of it is a pair. Each element is a pair of element. Means each element is a pair x and y, where x belongs to A and y belongs to B. Okay, such that x belongs to A and y belongs to B. So for every A, what are the ordered pairs possible between A and B? 1 and A, 1 and B, 1 and C. Because for every A, it will come, each element of A will come with each element of B. With the in this ordered pair, why it is called ordered pair? Because the first element of this pair has to be from set A, and the second element of this pair has to be from set B. So this pair is ordered pair, but because this is a set of ordered pairs, so okay, let me first write all of the possible ordered pairs. Okay, so all possible ordered pairs is 1 and A, 1 and B, 1 and C, 2 and A, 2 and B, 2 and C, 3 and A, 3 and B, 3 and C, right? So with A, A has to be paired with each element of B. So you have this. Similarly, 2 is also an element of A, and each element of A has to be paired with every element of B. So 2 will be paired with A, 2 will be paired with B, and 2 will be paired with C. That's what this is. And similarly, 3 will be paired with A, B, and C, and that's what this is. Okay. So a set A cross B set will be equal to all of these elements. And because it's a set, the order is not important. So each element is an ordered pair, but there is no order of it means each element is an ordered pair, but you can't say what is the first ordered pair, what is the second ordered pair. You know what I'm saying. So it can be 3A, 1A, in any order you can write it. So it's a set, but each element is an ordered pair where first element belongs to A, second element belongs to B. Now you may be thinking that what is the use of it? What is the use of this product of sets? One of the use is in the combinatorics actually. the multiplication rule that we will see very soon. The multiplication rule, the ways of doing things if you want to accomplish a task, and basically there's task T that you want to accomplish, but accomplishing task T means that doing T1 and T2. And let's say there are m ways of doing T1 and there are n ways of doing T2. Then how many ways you can do the task T? Okay. Should I explain multiplication rule right here? See, if let's say you have to accomplish a task T, and to complete task T means doing task 1 and task 2 both, and task 1, for doing task 1, you can do it in m ways. Okay, let's say x1 is one of the way you can do, x2 is another way you can do, and so on, so on. There are m ways to perform task 1, and there are n ways to perform task 2. Okay, n ways to perform task 2. Then if you, let's say, if you take any ordered pair, means that first element of this ordered pair has to be from T1, and second element from the ordered pair has to be from T2. Then any ordered pair is one way of doing T. Any ordered pair is one way of doing T, right? So if you take x1 y1, I don't know if it is visible or not. So x1 y1 is one way of doing it. x1 y2 is another way of doing it. Okay. So in multiplication rule says that if the number of elements in T1 is m and number of elements in T2 is n, then number of ways of doing T is m into n. This is a multiplication rule, because how many ordered pairs you will get is actually m into n. So number of ways of doing T is number of ordered pairs. Okay. And I am taking the ways, T1 to be a set. Okay, this is the fundamental of multiplication. T1, you can think of T1 as a set where each element is distinct way of performing T1, and T2 as a set means task T2. You can think of it as a set where each element is a distinct way to perform T2, and number of ways to perform T is the ordered pair between T1 and T2, ordered pair of T1 cross T2. Okay, number of ordered pairs of T1 cross T2. Okay, I will cover multiplication rule again separately. Just showing that how where it is applied. Actually, this is a fundamental rule of counting. There are two fundamental rule of counting: the sum principle and multiplication principle. Here, the constant is that for T to accomplish, both has to be performed in a sequence. Okay, in a sequence. First T1 has to be performed, and then T2 has to be performed. The sequence can change. Let's say there is another task T dash. For T dash, T2 has to be performed first and T1 has to be performed first. The number of ways would not change to perform. Then the number of ways for T to complete T1, T dash or T is same. That is m into n, because multiplication is commutative. But the ordered pairs will not be same. Okay, in to accomplish. So tell me, what are the ways to do T dash? The ways to do T dash would be now y1 x1, this is one way, y1 x2, this is another way, in this manner. Anyways, multiplication rule is not to be covered here. That's a separate topic of in combinatorics. Similarly, there is a sum rule. In sum rule, we will see how the union operation of set comes into play. Okay, so set is, that's why in the very first introduction to a set, I told you that the sets are very important, because building upon set theory, other concepts are derived, and set is very fundamental. Just think about what is a set. It's just a collection. So collection is a very fundamental thing. Anything, anywhere there is a collection, you can think in terms of set perspective. TOC is completely uh, like set membership. TOC can be summed up as a set membership problem. Anyways, so this is your A cross B. What about if there are three sets? What is the product? We are talking about product of sets. This is the product of two set is set of all possible ordered pairs. But what if you have three sets? What if you have A cross B cross C? A cross B cross C. Then this is a set of all possible ordered pairs. No, it is not pairs anymore. Means it's a set of an ordered entity, but that entity is a ordered tuple, three tuple. Actually, the ordered pairs means these ordered pairs are two tuple. You can think what is a tuple now? Right now, I will also relate it with a relational uh, database. So in database, there are different types of database, but relational database is is when you are storing your data as a relation, which is actually a table, and each row is called as a tuple. But each row can be think can be thought of, means it is based relational database is based upon the concept of relation only, and each tuple is actually a k tuple. For example, okay, before I explain, let me just write is a set of all possible three tuple, and I will explain what is a tuple. Okay, so let's see a case of a relational database or relation. If you are very new to the computer science and database is something that you have never heard of, then also you can understand it. Database is a uh, record keeping of entities, like, let's say, look at it. Let's say there is a university, and university is keeping a record of students. Okay, keeping a record of students. Then every student must have some student ID. It's like a register. Student ID, student name. Okay, subjects. Okay, so student ID, let's say first student is Gulam. Okay, and he studies subjects. The subject that he studies is computer science and engineering. And second student name is Moinuddin. Okay, and he studies, let's say, machine learning. Okay, machine learning comes under computer science. Artificial intelligence also comes under computer science. Okay, he is a master of physics. And there is a third student. Let's say his name is Ramesh, and he is a master of mathematics. Oh, sorry, he is a student of mathematics. Okay, and grade is that they are all are toppers, always A plus, A plus, A plus. Okay, so in this case, every row, each row is information about one entity, which entity is a student. So one row contains all the information about Gulam, all the information about this student. Second row consists of all the information about Moinuddin. Third row consists of all the information about Ramesh. And each row is called as tuple. Each row is called as tuple because it's an ordered quantity. Means the first element of this tuple is a number that indicates student ID. But if you just take out the tuple out, if you just take the tuple out, then first element has to be a number. Second element is a string, which is a name of the student. Third element is a string, which is a student subject. Fourth element is a okay, हटा दो, प्लस हटा दो, यही लिख दो, आउटस्टैंडिंग कर दो इसको, ओ ग्रेड. Third, fourth element of this tuple is a grade. So this is a four tuple. This is a four tuple. Something like this: one, two, three, four. Then you say it's a four tuple. If the order is important in this collection, then it's a tuple. So A cross B is set of all possible two tuples. Okay, set of all possible two tuples. Where so two tuples means ordered pair. The first element belongs always has to be from A. Second element always has to be from B. Similarly, in this case, A cross B cross C, this is a set of all possible three tuple. Three tuple means you had three elements in a tuple, where the first element always has to belong to A, second element always belongs to B, and third element has to belong to C. And all such tuples possible is your in your product of sets, you have all such three tuples. Okay, in database, when I will start, I will again explain this. So you can think in database also, each of this is called attribute. Okay, that student id is one attribute of the student. So this is your student table, then each of these is one attribute, is the attribute of a student. So you can think of every attribute as a set. Then there is something called as domain, that this set will have a domain. Okay, the content of your table is going to be a subset of cross product of each of this set. Means all of these elements are tuples, and they are a subset of cross product of these sets. A set student id set cross student name set, cross product with subjects, cross product with grade. Okay, let's complete this set of product of three sets. So this is equal to nothing but x, y, and z, such that x belongs to A, y belongs to B, and z belongs to C. Okay, so let me take one example to explain. Let's take A to be 1 and 2, A and B, and let's take C to be P and Q. Okay, you will see that the number of elements in A cross B cross C is going to be 8. Actually, the number of elements, the cardinality of A cross B cross C is equal to cardinality of A into cardinality of B into cardinality of C. Every element of A, all possible pair. So for A will be connected with, one will be connected with A, then A with P and A with Q. So one A and P is one three tuple, and then one A and Q is another three tuple. Similarly, one will be connected with B, and B will be connected with P and Q. Another two three tuples are one B and P, one B and Q. Likewise for two. Okay, so 2A and P, 2A and Q, 2b and p, 2b and q. Okay, so as you can count the number of elements, 1 2 3 4 5 6 7 8. So this is equal to number of elements in A is 2 into 2 into 2, which is equal to 8. So in general, so I have taken two cases, product of two sets, and I have shown that product of two sets is a set of all possible ordered pairs, which is a set of all possible two tuples. Product of three sets is set of all possible three tuples. Similarly, you can, let's say there are k sets. Then product of k sets is what? Set of all possible k tuples. Okay. And what is the number of elements in the product of k sets? It is equal to the cardinality of each set product of the cardinality of each sets. So when we have product of sets, the cardinality of the product of set is equal to just product of their individual cardinalities. I don't have to. I don't think it needs a proof. It's a straight. But let me show it. Let's take only. Let's take first two sets, and it will be easy for me to explain. Let's take two sets A and B. What is happening is that if this is your set A and this is your set B, then every element of set A is connected with every element of set B, right? So if let's say set B has m elements, n elements, let's say set B has n elements, then A has m elements. Then for every element of A in the ordered pair, in the set of all ordered pairs, each element of A is adding n elements. Okay, each element of A is adding n elements. So this is your first element, let's say A1. So A1 is adding n elements to the set of ordered pairs. M elements, sorry. Similarly, A2 will add, because then now A2 will be connected with each element of B. So A2 will also add n elements, and so on. All the m elements are going to add n elements. So what is the ordered pair? It is n plus so on m times, which is equal to n into m. Okay, which is equal to m into n. Now, if there are three sets, let's say there is another set A, B, and C. And C has, let's say, p elements. Now, your three tuple is going to be something like this, where these two, this place is for element of A, place is for element of B, and this place is for element of C. Now you that you already know that set of all possible ordered pairs means this part is going to be m into n. Let me just replace it with m into n. What I mean is that this is my A cross B. Okay, so of course this is going to be, let's say, one ordered pair A1 A2 and A1 B1 A2 B1 A2 B2. Okay, don't take it as a set. Why I'm doing so? Because then I will explain in a while that why I'm not doing it. I am just saying that your triplet is going to be like this: A1 B1 and something from set C, A2 B2 and something from set C, A3, B3, and something from set C, and so on, so on. How many such is possible? Means I am not filling this part. I am just looking for distinct these. So how many such? There are m into n such, right? Now to include this, we have to pick it from here, and for each of this, you have p choices. You have p choices. So it becomes in a similar manner. It becomes what? For first one you have p choice. For second one you have p choice, and so on, so on. For m into nth one you have p choice. So the number of elements become what? P plus so on, so on, p, which is equal to m into n into p. Okay. What about the product of four sets? Similarly, for product of four sets, what you will do? So for four sets, this is like principle of mathematical induction. If you were studious in your 11th and 12th, you would have understood this already, that we can apply mathematical induction to get the result. But I don't think that you were studious, just like me. So if it was four sets, then you know that there's going to be four tuple. There's going to be four tuple. Okay. So you know about, if you just take uh, if you just consider this region up to this, all the distinct elements in up to first three only, then you know that how many are those? M into n into p. And then for each such m into n into p, you have, let's say, for if you have a into b into c into d, if you have four sets, and let's say d has cardinality d, then for each such you have d choices, and then the cardinality of a cross b cross c cross d is nothing but m into n into p into d. Okay, so it's okay. Now let me just directly write. I have proven. So let's say if you have set a1, set a2, set a3, so on, so on, set ak. Okay, then this is the product of such sets. What is the cardinality of this? This is equal to cardinality of a1 into cardinality of a2 into cardinality of a3 into cardinality of a4 into so on, so on, cardinality of ak. This is the result. Okay, so product of sets is over. Let's get little bit about Cartesian product of sets. Actually, when you have only two sets, the product of two sets is also called as Cartesian product of sets. Why? Because think of Cartesian plane. Okay, let me explain. Cartesian product of sets. Cartesian product of A and B. It is just the product of two sets is also called Cartesian product, because you can represent the product of two sets in a Cartesian plane like this. Let's say this is one Cartesian plane. Okay, and this axis is your A, and this axis is your B. Means this axis will have elements of A, and this axis will have elements of B. Okay, let me take just A to be 1, 3, 5, and B to be 2, 4, 9. Then what is A cross B? How many elements will be there in A cross B? 3 into 3, 9 elements. So the number of elements in A cross B is equal to 1 and 3, sorry, 1 and 2, 1 and 4, 1 and 9, 3 and 2, 3 and 4, 3 and 9, 5 and 2, 5 and 4, 5 and 9. So this is 1, this is 3, and this is 5. And what are the elements in B? Elements in B is 2, let's say this is 4, and let's say this is 9. Okay, then you just plot it. So with 1, because we are talking okay, this is Cartesian product, so it is all possible pairs. So 1 and 2 will be everyone will have a point. So everywhere you will have a point everywhere. Similarly for 3, so this is something, the Cartesian product will be something like this only, because it is all possible pairs. Okay, in the next video we will read about relation. Relation is a subset of Cartesian product of sets. I will explain what relation is, but it's a subset. So subset means that some of the elements might be missing. Okay, even the Cartesian product of sets is also a relation. You know, the product of set, Cartesian product of set is also a relation, because every set, one of the subset of any set is a set itself. So this is also one of the relation. A cross B is also one of the relation. But relation is actually can be the proper subset also. So some of the, let's say that if you miss this point or this point, this is one of the relation. So this is the difference between Cartesian product of sets and relation, is that in product of set the dot will be or every possible dot, and in relation some of the dots will be missing, some of the dots may miss. In the next video we will talk about relation. Thank you very much. Just like in different set operations like union and intersection, we saw that commutative and associative laws, whether they hold or not. Similarly, in this video, let's look whether the product of sets obey commutative laws or not, or product of sets obey associative law or not. Actually, they don't obey, and this is quite obvious. I'm going to explain it, but it is also quite obvious, because A cross B is an ordered pair, a set of all possible ordered pair. But in the ordered pair, your first element is from set A, the second element is from set B. Now, if you keep the same set and just interchange the position, what you get is a P cross A. And so, but anyways, these two ordered pairs with interchange positions, that is x1 and y1, is one ordered pair. You just interchange the position, then these two are different ordered pairs. Okay, in ordered pair, order matters. It's not about the same elements, it's about what is the first element, what is the second element. Order is important in the ordered pairs. So these two are not equal. So if these two are not equal, then obviously A cross B is not equal to B cross A. A cross B is not equal to B cross A. Right? What is A cross B? A cross B is equal to an ordered pair of A and B such that A belongs to A and B belongs to B. Okay. Now to this set only, if you make B as the first element of the ordered pair and A as the second element of the ordered pair, means for every element in A cross B, if you are interchanging the positions of ordered pairs, interchanging the position of elements in the ordered pair for every such ordered pair in A cross B, then the new set that you are getting is nothing but B cross A. So B cross A is equal to this. Just for every ordered pair you are just interchanging the positions. So A belongs to A and B belongs to B. Okay, and you know that these two any two such ordered pair are not going to be equal, and so A cross B and B cross A can never be equal. So A cross B is not equal to B cross A. It's not that they can never be equal, but if A and B, if sets A and B have any one element which is not same, if either one of the element in A cross B, if either A or either B is phi, in that case they can be equal, because then you are not getting any element in the empty set to pair with. Means A cross phi is equal to phi, because you cannot pair the elements of A with any element in the empty set, because there is no element in the empty set, so you are not getting anything to pair with. So A cross phi is phi, or phi cross A is phi. So if any of A or B is phi, okay, if A is equal to phi or B is equal to phi, or B is equal to phi, then A cross B is equal to B cross A is equal to phi, right? Other than that, they will always be not equal to each other, except also when A and B are equal. If A and B are equal, then it is more like A cross A. So you can add this condition, that condition here, that if A is equal to B also, then A cross B is equal to B cross A. Okay, so this is it. So it's clear that product of sets are not commutative. Product of sets are not commutative. Product of two sets are not commutative. Product of two sets are not commutative. As a rule, they are not commutative. Means for special cases when A is phi, special cases when A and B are actually the same set or equal sets, for those cases the product is commutative, but that is a special cases. As a rule, they are not commutative. Actually, apart from this, they are always going to be not equal. So product of sets are not commutative, and A cross B equals to B cross A only when A is equal to phi or B is equal to phi or A is equal to B. Okay, let's look the associative law, whether the product of set obey the associative law or not. What will this give? This will give a set of ordered pairs, because this is one set, let's say S1, and this is another set S2. Of course, S1 is in itself a set of ordered pairs, and then this is a cross product. So this will give you a ordered pairs where the first element is an ordered pair and the second element is any element from set C. Means the ordered pair will be like this. First element is an ordered pair, and an ordered pair is paired with the element of C. Okay, so this is A, B and C. So A belongs to, or more like, ordered pair AB belongs to A cross B and C belongs to C. Okay, and this is a set of ordered pairs a set of ordered pairs because this is a cross product. The element of set A is being paired with an ordered pair. In the RHS, if this is your RHS and this is your LHS, in your LHS, the first element is an ordered pair. In your RHS, the second element is an ordered pair. So definitely they are not same. Okay. B and C and A, where A belongs to A and B and C belongs to B cross C. Actually, when it comes to product of sets, I can make it as complex as possible. Okay, like in this case, there is an ordered pair with an element of the set. I can just say that my C is also a set. Set can have anything. Maybe C is also a set of ordered pairs. Then what is the net result of this operation would be that an ordered pair is being paired with another ordered pair. Whatever the case it is, will not be associative. They will not be associative. Okay. So product of sets are not associative. Okay, I will explain the complexity again, but the result I'm going to write it right now. And let me take some complex examples of product of sets before getting into the relation. So product of sets are not associative. Okay. 1, 2, 3. B is equal to 4, 5. AB X, Y, Z. First of all, the number of elements in A cross B will be 9. So number of elements in A cross B will be number of element in A into number of element in B, which is equal to 3 into 3, that is equal to 9. Now let's list all those elements. So, or let's just write the set A cross B. Each element is going to be paired with every element. Every element of A is going to be paired with every element of B. So as you can see, this ordered pair will be 1 and 4, 5. Okay. Then 1 and AB. Then 1 and XYZ. Okay. Then 2 and 4, 5. Similarly, 2 will be paired with each element. So 2 and 4, 5. So here in B, every element is an ordered pair. Okay. No. In B, these two elements are ordered pair and this is a 3 tuple. In a set, you are just having distinct elements. Those elements can be anything. Okay, in a set you can put a cat and dog. A cross B will give you a set of ordered pairs. An ordered pair is something where you have two elements in order. And what are those two elements going to be? They can be simple a number. They can be themselves an ordered pair. They can be 3 tuple. One of them can be 3 tuple. Both can be 3 tuple. I can just add one element in A, which is a 3 tuple. Then that 3 tuple and an ordered pair will be paired into an ordered pair. Okay. So you just need to know that what is happening is that each element is being paired with every element of the other set. Means the second set, means if this is A cross B, then elements of A is being paired with each and every element of B. Now the element of A can be anything. The element of A itself, that element can itself be an ordered pair or a 3 tuple or any k tuple. Okay, the in elements of B can be anything, but then these two things are being paired. Enough of it. I am going to just explain, write this and end this video, and in the next video I will start relation. So 2, 4, 5, 2, A and B, 2 comma xyz. 3 comma 4 5, 3 comma ab, 3 comma xyz. Okay, let's take one more element in A, just for the sake of doing it. Let's take this also some k tuple, some ordered pair. Let's say I'm taking it as C and D, and let's take some 4 tuple, PQRS. Okay, then the CD will be paired with every element. So as you can see here, this is an ordered pair in which each element is an ordered pair. Now let's end this video here. In the next video, I will start with the relations. Finally.